Hello everyone, I'm Bowen. Today I'm going to give a brief tutorial about assignment 2, the third and the fourth problem, which is the minimal spanning tree problem and the minimal gas stop problem. So now let's begin. The question 3 is a minimal spanning tree finding problem, and it gives 5 different rules of finding a minimal spanning tree, and asks you to judge which one can lead to a correct answer. And here's two crucial parts that need to be noticed about this problem. That is, first, it doesn't have any restrictions on finding a card. So that means any card available is all acceptable. It's all valid cards. And also there is no tie-breaking rules. So these two parts can help you to find out the valid counterexample. And also let's review the 5 problems. The first problem is that it will find the latest edge from a card and add to the minimal spanning tree. And the second problem is adding a rule that after finding a minimal weight edge, it will delete that edge from the original graph. And the third one is that when the lightest edge is found, it will contract. It will make edge contraction. And the fourth method is to delete the heaviest edge from graph. The final one is about vertex incident. Now let's look at them one after another. Question 3a is find the card and add to the minimal spanning tree with the lightest edge in X and no further procedures. And I found many students made mistake here. That is because they didn't take the tie breaking rules into consideration. So here's a counterexample. So here the above part is the original graph, and the lower part is the minimal spanning tree that it will generate. So for this kind of graph, once we make a cut here, and it will add the lightest edge with it, which is this edge, and then we cut like this. When in this case, these two edges are tie, forms a tie, so we will pick the lightest edge randomly. So in this case, we will maybe we will pick this edge, and next time we still use the same cut because we don't have any restrictions on choosing a cut. So then we will form this minimal spanning tree, and this is different to the ground truth minimal spanning tree. So this is a intuitively counterexample. Again, the most important part of this problem is that there is no tie-breaking rules of the original problem, and also any cut available will be valid. So that's why this counterexample would happen. The statement of question 3b is to find the cut X and add to the generated minimal spanning tree with the lightest edge E from all the cut X, and also it will delete the edge from the original graph. So this is also an incorrect algorithm because it will have the potential to form a cycle in the generated minimal spanning tree. So we, as before, the above part is the original graph, and the below part is the generated minimal spanning tree. And first, let's make a cut here, and we will add the lightest edge, which is this edge, to the minimal spanning tree, and we add another cut here. We will add the lightest edge, that is this edge, to the minimal spanning tree, and we will delete this edge, and we make the cut that have the same that lies on the same place. So in this case, we will form a cycle in the generated minimum spanning tree. So we don't need to go any further because a minimum spanning tree cannot have any cycles. So that's how we generate a counterexample about this problem. Question 3C is the only correct algorithm, that is to find the cut x and add to t a lattice edge, and then contract that edge. So the edge contraction means, for this example, that this edge is selected. To contract that edge, it will merge the two endpoints of that edge into a single node, that is here. And then the original graph will be changed into a multigraph, that is, have multiple edges between two endpoints. This edge contraction algorithm is correct because this algorithm is equivalent to the blue edge coloring rule that Professor have already proved at around week 6. So in this case, proving the correctness of the edge contraction rule will be very easy because as long as we have proved the equivalence between the edge contraction algorithm and the blue rule algorithm, then we can prove that the edge contraction algorithm is correct because we have already proved that blue rule algorithm is correct. So the method to prove the equivalence is mainly formed by two parts. So the first part will be proving that this algorithm, edge contraction algorithm, will end after n-1 iterations. And the second part will be that for each iteration, the two algorithms will have the same cut set, so the outcut available or maybe possible will be always the same. So in this way, we prove that these two algorithms will be equivalent. Now let's look into this example. So here's our original graph, and we make a cut here. So we can apply blue rule like this, and we can also apply the edge contraction rule like this. And for this cut, this edge will be colored blue with blue rule, or it can be contracted into one node like this, and then we will add another cut here. Then the cut we added will be the same among these two rules, and apply the same method again and again, and we will form a minimal spanning tree that is equivalent to the ground truth. And also for each iteration, you can, for the edge contraction algorithm, maybe this is not very intuitive, but you can view the generated minimal spanning tree just as the blue edge. Now we will look into the actual proof. So the first part is rather intuitive because for each time we contract an edge, then the two endpoints of that edge will be merged into one. So the overall node of the original graph will be reduced by 1. And after n-1 iterations, there will be only one node left. Then the algorithm will terminate. So the first part is proved, and for the second part, that each iteration the two algorithms will share the same possible cut set. This is also true because we can argue that as we know the blue rule, once we have colored that edge blue, we cannot cut that edge anymore. That is, the remaining cut set is that all the cut except the cut that include the blue edge. So for example, the original cut set in this graph that none of the edges is colored blue will be S. And once we have colored some edge blue, then all the cut that will include this edge to be colored blue will be excluded from the original cut set. So this means say that the original cut set will be S, then all the cuts that include the blue edge will be S slash, and the remaining cut set will be S minus S slash. And for the edge contraction, the condition will be the same because once we have contracted edge like this, and then all the cut that will include the contracted edge will be excluded from the original cut set. So the remaining cut set will be the same for these two conditions. That is, the original cut set minus all the cut that include the edge that is colored blue or contracted. And you will find the more formal proof in the homework solution. So in this way, we prove that the edge contraction is equivalent to the blue rule. So that forms the proof that the edge contraction algorithm is correct. Question 3D is quite simple because we will leave some edge isolated. So the algorithm is delete the heaviest edge of X from G. So for the original graph, we first will make this cut, and we will delete this edge, and we make another cut. We will delete this edge, and finally we will find that these vertices will be isolated. Question 3E is also incorrect. So the algorithm will be find out some vertices that is not incident with any blue edge and color the edge that is incident with that vertex that have the lightest edge to blue. So many people made mistakes in this problem because they didn't take into this situation into account. So the above part is the original graph, and the below is the generated tree. So first we will select this vertex and select the lightest edge, that is this edge, and color all this vertex and this edge blue. And then, as the algorithm stated, we will find a vertex incident with no blue edge. So in this case, we will select this vertex and then color the lightest edge incident with this vertex blue. Then, following the rule, we will choose this edge. Then we have colored all the vertices blue, and we will select no more vertices. There is no more vertices available. So this algorithm will terminate as this part. Then it will never form a minimal spanning tree. I think many people made mistakes here because they hold the hypothesis that all the new generated new colored blue edge will incident with the former blue edges. Now let's look into the question 4, that is the fuel gas stop problem. So the problem states that you will travel from A to B, and your car can only travel k kilometers after each gas stop, and you want to make few gas stop as possible. So this problem will have two different versions. The first will be the past version, and also we can look into the graph version. And the correct analysis of any of this version will be acceptable. So now let's first look at the past version, that is viewing the way between two places to be a single pass. So the solution will be a greedy algorithm that we will find the furthest gas stop to stop every time we start our trip from the previous gas stop. So that means, say, we start at A and then we can only travel, for example, 8 kilometers. Then we will find the very last gas stop that we can reach from A. And we repeat this method again and again. So next time we will stop at maybe this gas stop, and we will find out the last gas stop that we can reach from this gas stop. The algorithm is as follows. So DI means the distance from A to the S gas station. So for maybe PI, the respectively DI will be the distance between A and PI, and for P2, the D2 will be 3 plus 1, which is 4. And then for the P3, the D3 will be the 3 plus 1 plus 6, that is 10. And the capital S, will record all the stations that we will stop. That is maybe S1, S2. And the lowercase p will be a pointer of the previous stations that we stop. So here's the whole algorithm. So we will iterate our algorithm over each of the gas stops. And this part means that we will compare the distance between the previous gas stop that we stopped at with the current gas stop that under investigation, and we calculate the distance between these two stops, compare with the capacity that our car can travel, that is k. And if the distance is larger than k, then it means that we cannot travel from the previous gas stop to the current gas stop that we investigate, and we will do the following procedure. And since this will be the first gas stop that we cannot reach from the previous gas stop, we can subtract the current index by 1, which indicates the furthest gas stop that we can reach from the previous gas stop, and we will use this gas stop as the one that we stop at. So more intuitively, we can look at this as an example. So you can ignore these two parts, which we will use as proof. So first, we will start at station A, and then we will investigate all these 4 gas stops, including B. So first, we will initialize the S as empty set. The previous gas stop will be A, and then we will investigate this gas stop. So the DI minus DP is 0. So DI is 3. So DI minus DP is 3, and P and S will not be updated. Then we investigate the station 2. So D2 minus DP will be 4, which is 3 plus 1. The DP is still the station A, and P and S will not update. And then we will investigate the gas station 3. So in this case, the DI minus DP, DP is still 0, while DI will be 10. So in this case, by this rule, we will conclude that we need to update the previous gas stop, that the current index I is 3. So the P will be updated as 3 minus 1, that is P2. So and then P2 will be added to the record of the gas stop that we stop at. So the S will also be updated. Next, we will look into the gas stop P4. So currently, the previous gas stop will be the P2. So then D4, that is this length a to P4 minus dP will be the distance between P2 and P4, that is 11, which is also larger than K, that is 8. So we will also add the P3 into the stop set, and we will assign P3 as the previous stop. Then next we will look into the destination B. So distance between the previous stop, that is P3, and B will be 7, which is lower than K. So we will not update the previous gas stop, and the S will also not be updated. So that forms the algorithm. Then we will prove the correctness of this algorithm, and the overall method is the rule of induction. So first, let's suppose that this algorithm returns a solution set that is S1, S2, S3. For this particular case, the solution will be S1, S2 that we stop at, which is P2 and P3 respectively. And we should know that there are more than one optimal solution for this particular case. So, for example, we can always choose another optimal solution that we stop at P1 and P3. This is also valid, and the number of gas stops doesn't change. The thing we want to show is that among all the possible optimal solution for each particular case, so for this case, the optimal solution will include this solution and also this solution. So for all this solution, we will always find one solution that contains the first element of what this algorithm returns. And in other words, we need to prove that what this algorithm returns will be one of the optimal solution for this particular case. So suppose the optimal solution that we select is this solution, that is P1 and P3. So since our algorithm will return the furthest gas stop that we can reach from A, then the solution, the given optimal solution, the first element of the given optimal solution will always be the former gas stop of S1, or at least equal to S1. So then for this optimal solution, suppose we delete the S1 star and we add the S1, then this is also an optimal solution. So if we exchange this the gas stop, the first element in the optimal solution gas stop to what the algorithm returns, then it's also the optimal solution. And once we have changed this S1 star to S1, then we can view this S1 as the starting point of the later gas stops of the later route. And by the rule of induction, we have proved that what the algorithm returns is also an optimal solution. And you can also check the homework solution for further details. And finally, let's look into the relatively tricky part of question 4, that is a graph version of Fewey's gas stop problem. So the graph version means that there are multiple paths between A and B, and we will look into a path. We will need to find a path that we can stop, that we can make the fewest gas stop. So my method is a modification of a Dijkstra algorithm. So the professor have already introduced the Dijkstra algorithm in his lecture, and the very crucial part of this Dijkstra algorithm is the distance a metric that is the distance from the source node to the node under investigation, which is denoted as this V. And we can also define another metric that I denote this as capital D subscript by A and B. So DAB is a metric between two endpoints in this gas station graph. And DAB means the metric between starting point at A and the stop at B. So it will include two parts for comparison. So the first part is NAB, and NAB will be the number of gas stops needed from A to B, and it will include the starting node. So for this specific example, so say we take this path, so A to 1 to B, and since we will have to stop at 1, then the DAB will be number of stops including the starting point, that is the A, and stop at 1, so 1 plus 1 is 2. So NAB, if we take this path A to 1 to B, will be 2. And FAB will be the distance left to drive after stopping at B. This means that, for example, if we travel from A to 2, to node 2, then if we stop at 2, there will be 7 kilometers left to drive. So FA2 will be 7. And after we define this metric, DAB, then we will replace this metric with the distance of V in the Dijkstra algorithm, and we will form our own algorithm. So you can refer to the professor's lecture at around week 9 that he introduced the Dijkstra algorithm as reference. So my algorithm is actually totally the same with the professor's algorithm. So the only difference is this several part. So the first part is initialization part, and there are two rules need to be defined to replace our metric with the professor's algorithm. So the first part is a rule of comparison because the professor have used distance comparison in Dijkstra's algorithm. So we can define DAB bigger than DCD by this rule. So first we will compare N, so the first element of DAB. So if number of stops that AB have is bigger than number of stops that CD have, then we will directly say that DAB is bigger than DCD. And if we have the case that NAB is equal to NCD, then we will compare the later part. However, this part we will use a reverse rule. So if FAB is lower than FCD, then we will say DAB is bigger than DCD. So this is rather intuitive. So the metric between AB is bigger than CD only when the number of stops that AB will need is more than CD will need. And if the gas that we left after we stop at B is lower than gas we left from stopping at D, then we would say that we need to travel further by taking the path AB. So in this case, DAB is also larger than DCD. So that's a rule of comparison. And we need to stress that for N, the comparison is ascending order, and for F, the comparison is descending order. We also define the rule of adding. So there are two cases. So if FAB plus FBC is larger than K, then in this case, this is a case that after we stop for maybe A to 2, then the gas left is still capable for us to travel to the next node. So in this case, we will add this to DAB plus DBC by this rule. So we doesn't change the number of stop after stopping at B, because we don't need to stop at B. We can directly travel from A to C, and the distance that we left is calculated by this formula. And for the case that after we stop at maybe A, so we can take this path as example. So maybe we travel from A to 1 and 1 to B, and after 1 we don't have enough gas for us to reach B. So in this case, the FAB plus FBC is lower than K, and in this case, we will update the DAC by this rule. So we stop. We will make another stop actually at B point, and the gas left is what we start at B. This part is a little bit wordy, but I will illustrate now the idea with an example. And this two part is mainly defining the rule of comparison and the rule of adding. So how this work is to define a new metric in replacement of distance V, that we can regard the number of gas stop as a crucial part. And here's the overall algorithm. So we first initialize the distance in source as a tuple of 1 and 8. That means if we start at A and stop at A, then the gas stop we have will be only 1, and the gas we left is 8. And just like Dijkstra's algorithm, we will initialize all the metrics on other node to be infinite. Then for convenience, we will calculate all the metric of each edge. So for maybe edge A1, the calculated DA1 will be, since the edge length is 3, then the gas left when stopping at 1 will be 5. So the FA1 will be 5, and NA1, since we only stop at we start at A, so the NA1 is 1. So the same case for each of the edge. Then just like the Dijkstra's algorithm, we will look into the node that have the lowest metric. So among these 5 nodes, we can easily notice that the node A will have the lowest metric. So we put this node A into the S. So S is the set that we have finalized its metric. And in this case, I have a color in as red. And for this node that has been newly added into S, we will find all its neighborhood that the nodes have not been added into S, and we will calculate its metric. So this part is relatively simple, so I will skip this part. So to calculate, sorry, we can look at the previous slide. So to update the metric of A to 2, we will add the tuple 1 and 8 with the tuple 1 and 7 following one of these rules. And for this particular case, 7 plus 8 is larger than k, which is equal to 8. So we will update this node DA2 following this rule. So the DA2 is equal to 1, 7, and the same case for DA1, that is 1, 5. And among all the nodes that have not been added into S, we will compare all its metric. So among these 4 nodes, we will compare its metric. The one is node 1 will be 1, 5, node 2 will be 1, 7, the other 2 will be infinite. So among this rule, by this rule, we can find out that the node 2 will have the lowest metric because it will have the lowest n, and since f2 f of the node 2, that is fa2, is higher than the f of a1, then we will conclude that this node have the lowest metric. So we will put this node into set S. And the same procedure will be repeated. So this node 2 is newly added into S, and we will measure the metric of its neighbors except the node that already have been added to S. So we will investigate the node 1 and node 3. For node 1, we will look into this path because node 1 is started from A to 2 to 1, comparing it with node A to directly to 1. So we add the 1, 3 is this part, and 1, 7 correspond to the metric from 2. So adding this equals to tuple of 1, 2, following this rule, following the first rule. And we can compare that, we find out that the result, which is correspond to this path A to 2 to 1, is further than the path between A to 1, that is tuple of 1, 5. So we will not update the metric of node 1. And for the node 3, for the same reason, we will calculate the metric from A to 3, that is A to 2 to 3. That is adding the metric from 2 with the metric of this edge, which is corresponding to this rule, and the result, the adding rule, we will use the first rule, and this is lower than the infinite, so we will update the metric of node 3. So here's the result of applying this procedure. And next step will be looking to all the remaining nodes and find out which one have the lowest metric distance from A to the respectively node. So we can easily find out that node 1 is having the lowest distance. So we will push node 1 into our set S. And we add this minimal path tree into the so-called T. Then, as before, we will look into all the neighborhood that node 1, which is newly added to S, have, which is 3, and node B. And we will calculate the metric of each of these two nodes. For B, we will add the 1, 5 with the weight of D1B, that is 1, 1. And the result will be 2, 1, which is smaller than infinite. So we will update the metric of B. And we will also calculate the 1, 5 plus 1, 6, that is equal to 1, 3, which is lower than 1, 1. So we will also update the metric of node 3, both because of this update rule. And here's the result. And again, we will look into the node among these two that have the lowest metric, that is node 3. So we will add this path into the minimal path tree. And then for node 3, there's only one node that it can reach from 3, that is B. So we will calculate the metric of this path. So that is from A to 1 to 3, and 1, 3 plus 1, 4. This is equal to 2, 4. This is because 3 plus 4, according to this rule, is lower than 8. So this means that after the car is traveling from A to 1 to 3, since the car only stop at A, it doesn't stop at 1, so there is only 3 kilometers for it that it can left to drive. So the remaining fuel is not enough for it to travel to next stop, which is B. So it will have to stop one more time at 3. So the result is 2, 4. So it will refuel at 3 and then travel to B. So there will be 4 kilometers left. That the result is 2, 4. And this is lower than 2, 1, which 2, 1 is corresponding to A to 1 to B. Therefore, the metric of node B will be updated as tuple of 2 and 4, like this, and we will easily add the final pass of the minimal pass tree, between the node 3 and node B, like this. So again, the whole idea of this solution is modification of Dijkstra algorithm, which is to define a new metric DAB in replacement of distance of V in Dijkstra algorithm. And that's all for today's tutorial. Thank you for listening.